All right, so I did a search for AP Physics homework something something, and I filtered it to be this week, and I've got this one here. Looks like going to work an old problem from the AP exam, so very cool. Let's see, I'm not sure, never sure where to put me, but this is number 30, by the way. This is pretty exciting to have done 30 of these. I got to tell you, I really enjoyed doing it. So here we go.
Okay, so let's see if I can do and explain this one in about 5 minutes. Just part A of 2018 Mech 3, just show how I can do it. And so tomorrow, what I want to do, you'll have some other stuff to work on. Would you like to take in-class AP? Do you want to take a free response quiz I mean a multiple choice quiz that's like either curved or correctable? Maybe we should vote on that too. You don't care. Correctable is better. I need some feedback from you. Like, are you ready for a little more stress of a curved quiz? Because you've been doing well so far. You should probably bet on yourself. I think you'll do well. Or are you just so stressed out now, closing out the end? I need a correctable quiz. I don't want to take any risks. You're in the.
So I really like how he's sort of empowering the students to really think about what helps them most. There's the content, and there's you holding them responsible, and then in an AP exam a class, there's this exam waiting at the very, very end. And so I think it's really great to put into the hands of the students, like, look, I could do this or I could do that. What I used to say is we can use in-class time for this, but that means outside of time class has to be that. Where is it best to have me right there for you to help you? So I really think it's great how he's doing that.
You're the student, so it really matters how you feel and how you perceive things.
Wow, this is a tough problem.
Okay. Using integral calculus, so I have to write an integral. Show the rotational inertia of the rod is ml squared, 1/2 ml squared, not what it normally is for a rod, which would be 1/3 ml squared. How's that possible? Well, it's weighted.
Yeah, so before he even says, I'm going to try to take some guesses here. So about its left end. Okay, so the left end here. Yeah, so you've got a little bit more weight away from you. It should be harder to turn this sucker. So I would expect it to be a bigger number. So 1/2 is bigger than a third. I heard a funny story that Wendy's hamburgers didn't sell that well because people thought that a third pound was smaller than a quarter pound because 3 is smaller than 4. Anyways, I think that's funny. Yeah, so this should be harder, right? The moment of inertia, there's so many ways to describe it. Someone had a really good one. I'm trying to remember exactly how it went. It was basically, how hard is it to spin you around, right? And so these things are going to be, it's going to be harder to spin the sucker around than it would be just a normal bar. So I also think it's amazing that it has a non-uniform linear mass density. So it also gets heavier and heavier and heavier the further out it goes. So it's not just that it gets wider, although maybe this is basically taking that into account. Maybe this nonlinear mass density it's a uniform density material. It's just literally getting fatter. I guess I'm not sure. I guess I would expect it to be proportional to x. So yeah, so this is a really interesting problem.
Weighted toward the end. It's really more like a wedge. Okay, and watch out. So this lambda is its linear density, and what I have to point out is this means that dm for a uniform rod would just be capital M over capital L times dx, right? Yeah. That means that dm is always just lambda dx.
Okay, yeah, I love that.
Whoa. Why do we need dm? That's what I have to say this, or for my due diligence in teaching. It says on the equation sheet that the real rotational inertia is r squared dm. Okay, and that's how you should start this thing, using integral calculus. There's an integral, and there's rotational inertia. I better start from that step. Okay.
So an interesting question is, how often does he listen to his own videos, right? Because there's some audio going in and out. I mean, I'm able to understand him the whole time. It's not really a problem. But, and I know this happens to me too, right? If I lean towards the computer, lean away from the computer, I'm sure I'm causing some audio differences. But honestly, I don't go back and watch all of my videos. So what will sometimes happen to me is a student will say, did you know that we couldn't hear that? It's frustrating, right? When you don't realize it. But sometimes it can be funky hardware and software too, right? So he's using something. Let me move my head here. He's using whatever the heck this is to record these, and who knows, maybe that could have some wonkiness to it. I really, really liked what he was doing here. He said, look, often this is super, super boring. But really, this is the whole story for every single teeny tiny mass. I'll find out how far away it is, square it, and add it all up. And we have this really, really interesting expression for lambda. I actually think this problem would be more interesting if you just said it was a triangular wedge made of a uniform density material, because then you have to figure this out first. So I'm not sure why the 2 would be there. It's because it's triangle. Yep, I bet you that's why there's a 2 there. Because of the 1/2 base times height. That's my guess as to why that's there. So I really loved how he connected that to the fundamental definition of moment of inertia. And really, the fundamental definition of moment of inertia is mass times r squared. It's just that it's a linear thing that can be added up. And so that's what the integral is good for.
Okay. But it's important to know too. So okay, that actually means move my little bar out of the way. DM.
And now I gotta move my face out of the way.
DM. Integrate over mass. That's nuts. We have to do something reasonable. We take 2m over L squared x dx. Okay, there's a bunch of constants times x dx. I can do integrals on x of monomials with x. No problem.
So I'm stuck on that factor of 2 again. If you just integrate dm, right, you'll get all the mass. So I would have expected all the mass to just be m. So if I integrate that, x goes from 0 to L. I'm going to get L squared over 2. Yep. Okay. So this will absolutely turn out to be that the total mass is just m. So that's you need that factor of 2 for sure. Okay, cool. Sorry that I have to keep moving my face.
Okay. So we're going to show this to get the rotational inertia. So this is basically, and part of, I'm having you do this, part of the one on the test is just, can you set up this integral and make a reasonable attempt at it? It's not the wedge, it's a different one. But okay, so I'm going to integrate from x goes to 0. I don't think you really need the x there. And now look out here, where's my mess? I have to do 2m over L squared x. That's part of my dm. I still need my r squared, which is x squared dx.
Yeah.
Okay.
So it's interesting, right? I mean, I think he paused there because he realized he should have written x squared first, right? Because then just, so that it's in the same order. R squared probably should have had the x squared, and then he's already said that dm is all the rest of this. But of course it doesn't matter, right? What is that, the commutative relationship? And so it doesn't matter which order you get this. And finally, I bet you when you get to here, the students are like, oh, man, I can do those in my sleep. And what's amazing is, we're going to have this cube here, and this means things are going to be raised to the 4th power. How could it possibly be as simple as this? So let's just check the units here. We got mass. Well, that's going to that'll be there for sure. We got length. We've got 4 of them because dx has units. Oh man, that just blows so many students' minds. dx has units. So we got length. So 4 of them, and then 2 of them down here. Oh yeah, we are going to end up with just 2 lengths. So cool.
So it's an x cubed integral. That's probably the first thing we could miss, and I'm sure they'll have some points for not getting the correct answer this time.
So he erased that because he wanted to pull some stuff out, right? So he had the integral sign. He's like, oh my God, I just want to pull the 2m over L squared. So he erased it, started again. Very cool.
We can look it up later. So all those constants come out. I'm really integrating x cubed dx. Should be easy by now for you calculus students, from 0 to L. Okay, yeah, you can do that antiderivative, evaluate it. Okay, we hurry. That's why it will only take me 5 minutes, because I don't have to explain how to do that. Okay.
Okay, so I'm going to stop right there. That was a really, really cool problem. I love how he's being such a great cheerleader for them. Like, you can do this. This is stuff you know. I think that the hardest part about this problem is that dm stuff. Is so subtle, especially when we do so many problems where dm is super easy, right? Where it's just m over L, in this case, m over L dx. And it's like, there's always this m over L. And suddenly you hit this sideways one that says, well, hang on a second. No, that's not how it works. The further away you go, the more mass is over there. So I really liked how he sort of broke it down and then said, okay, hey, these are all tools that we know how to do, and slowly worked it out. And as he said, you end up with an integral that's going to work out, because we're going to get a factor of 4 down in the denominator, which is going to cancel a little bit with this 2, and the L squared is going to become L canceled out by the L to the 4th you're going to get over here. So it's all going to work out and get you the answer that you want. So very, very cool. Well, hey, everyone, 30 of these. Thank you so much for sticking with me. And remember, physics teachers are awesome.